I'm a performance engineer at Netflix down in California, Los Gatos, where basically we do all product development, so all engineering and everything that is necessary for the product to work. And I'm here to share today a little bit about why we actually developed a real user monitoring solution. Most people don't, right? A few of the gotchas, a few of the issues we had to face during the development of that, and how it really helped us improve the experience to the user. So, going to that. First, a quick show of hands. How many of you are customers or at least know how Netflix works or what it does? Okay, good. So I don't have to go through the whole explaining what it does. So it's streaming service, movies, TV shows, all that stuff. It makes it a bit easier for me. I mentioned I work in performance, right? And when I'm talking about performance, size does matter, right? Scale matters, because only at scale you'll surface a lot of issues. Everything breaks at scale. So nothing better to talk about scale than by numbers. So I'll share a few Netflix numbers just so you have an idea about the scale that we are talking about. So as I mentioned, we just last quarter, I think, closed a bit over 139 million subscribers. And that's worldwide. Netflix works everywhere, every single country on the planet except a few countries in embargo and China. So global app, you can open your own account in Bermuda while you're traveling, and you'll get exactly the same experience, just a bit different catalog, but it's a global product. Those users, those subscribers, they watch over every single day. They watch hundreds of millions of hours of TV shows and movies every single day. I don't have the peak numbers from last year, but 2017, I think our peak day was over 340 million hours of content in a single day. So a lot of video, mostly HD, 4K, so a lot of video content. I remember some publication a while ago mentioned that some peak hours would consume more than a third of all internet traffic. So a lot of bandwidth. Most of those video bits, they get shipped to the users. They get sent to the users through our own CDN that was purposely built for that. That CDN, it handles tens of terabits a second of video bits, just purely video bits, something we have to deal with. Our users, daily, we have tens of millions of devices that talk to our backends every single day. We have a lot more registered devices, but these are just devices that talk, unique devices that talk to our backend services every single day, user devices. And not just those normal devices you might need to handle, right? Your iOS, your Android, your web. We have to deal with a lot of weird stuff. We need to deal with smart TVs. We need to deal with Chromecast and your PlayStations and Xboxes and some weird cable TV box in Belgium running Windows CE. We need to deal with that. There's a Netflix app running on that, and we have to make it work well for users under those conditions. So thousands of different models of devices. But when I'm talking about performance, it's performance of what exactly, right? Performance of the product. And for us, different from a few orgs, a few companies, we don't have a separate business or product organization and an IT one. We have one large product organization that takes care of all product development. So all engineering happens there. And for us, product is simple, is the streaming service that some of you know. And everything that is required to make that work. So all the backend services, all the storage, all the infrastructure, networking, code running on your phones, everything is required to make that work, that experience to the user. Our goals in the team, they are pretty broad. Performance is a pretty broad term, I would say, at least for us. So we try, first thing, we've been growing a lot. So we want to make sure that our service can scale with our user growth. We don't want to hit a point where, okay, yeah, we're kind of screwed. We can't really take more users. It's generally not a good thing to do. Old slide, but we want to make sure that everything, we can keep growing, can keep scaling, right? We also want to make sure that we are growing our cost sublinearly compared to our user growth. We don't want to grow costs faster than we grow our users, right? So we do a lot of work optimizing all the backend services and a lot of things just to make sure that we are not growing faster than the users. And it hasn't been that much of an issue, but it is a big, big portion of what we do. Primarily, one of the most important things, we want to avoid that spinning thing. Terrible experience to the users. You decide to watch Netflix, you open an app, whatever device, and that spinning thing just keeps spinning, and you give up and go do something else. Terrible experience. We want to make sure that it goes as fast as possible. You guys know that better performance, better customer experience, better retention, better acquisition, and all those. So direct connection to results. Same applies to this. You finally found something to watch and you click play and that thing keeps buffering and takes a long time buffering, doesn't go anywhere. Terrible experience. And plus, when you start playing, there's a lot of rebuffering, so we want to avoid that happening. So we work a lot with the CDN team on trying to optimize that and everything that's required. Also, a lot on reliability. It doesn't matter if it works fast if it doesn't really work at all. So if you try to do something that just doesn't work, you click a button, whoops, something went wrong. I'd try again in a few minutes. Terrible experience, especially if it happens frequently. Especially in our case, given our scale and that we are a consumer application. Because whenever something goes down, especially for a large number of devices and a larger region, this happens. You guys have no idea the outcome and what we see in social networks and everything else. Like, things explode really quickly. For some people, the world just ends when Netflix goes down. They have to sit down and kind of talk with the relatives, and we really avoid people doing that. So luckily, it hardly happens these days, right? We put a lot of effort the past few years into improving reliability, so it hardly happens, especially to a larger number of devices at the same time globally. It is pretty rare these days. And we do that, at least on the performance engineering side, all the way from kernel. So we do a lot of tunables, we work a lot of modules, we have hundreds of thousands of instances running the Linux kernel, Ubuntu, on AWS. So we do a lot of work on that side, all the way to the code running on your device. So in everything in between. So it is a fairly large scope, I would say. And we're a tiny team. I think we have 5 or 6 engineers to deal with all of that. So our focus tends to shift pretty often. In the past, I worked a lot on backend services, trying to optimize those. I built a lot of tools. A lot of them now are open source. So in case you guys want to try it out, there's a lot of stuff we build in the team that you guys can use. But the focus of today's talk is really the device. So how do I actually optimize that? And it's directly related to the user experience. First, independent if it's back-end, front-end, devices, or whatever methodology you're using to optimize something, it usually starts with you trying to understand what's going on, right? Trying to understand what's going on in the system, the devices specifically in this case. And I can't really understand what's going on if I can't see what's going on, if I don't have the right metrics. So it's really important for us to collect the right metrics, the correct metrics, so we can understand what's going on and can go then and optimize things. Important too is for us to be able to quantify performance, putting a number to it, right? Super important for automated systems, anomaly detection, your alerts and all that stuff. Helps a lot when I'm comparing something to see my progression over time, if things are getting better or getting worse. Putting a number to it generally helps. Makes things a bit easier, so important. One way of solving that, and then a lot of people do that, is just have a lab. Right? I get a bunch of devices that kind of represent what my users have. I put it in the lab. I use some sort of test harness that will try to reproduce some sort of workload there. I try to reproduce some network conditions maybe. But for us, that just it doesn't work really well. We have just too many variables, just too many devices, too many network conditions, both like conditions we know of and conditions we just don't know of, to rely only on labs. We do have a bit of lab testing, but we really want data from real user devices. We really want to understand what's going on at the user end. And there's a lot of stuff you don't even think of. Is the user's device, like Android device, using a lot of memory, so we're getting flushed all the time? There's a lot of stuff you don't even think can happen. Just it really happens in the field, and you can't reproduce that in the lab. So simple, right? There's a lot of third-party services today that do exactly that. You go to a website, you sign up, you get a JavaScript thingy, you put on a web page, you add a timer, and boom, you just start getting your nice dashboards and metrics. You didn't have to do much at all. Unfortunately for us, that doesn't work. It's not that trivial, that simple. Besides the issues with scale, like most of those services were not built with our scale in mind, with the amount of data we are shipping in mind. We also have the issue with device diversity. Most of those just work in a handful of different devices. They would not run on Windows CE. That we have to deal with that. And I don't want to compromise. I don't want to just ignore a few devices and just focus on a few. I want to really get a good grasp of everything and what my users are feeling. I don't want to neglect anyone. So there's bit. Netflix also is everywhere. So I have to deal with a lot of different network conditions. Devices will perform very differently on different network conditions. Netflix is a very network-intensive app. So I need to take that into account, both in the logging bit. I can't just keep sending beacons all the time because that will cause probe effect and affect my users. But I also need to be able to slice and dice and try to filter those. Hey, this is only happening in that tiny ISP in Cameroon when that user is talking to the wrong AWS region. I need to be able to tell that. So really important for us. Well, we decided to build our own, which is not uncommon for Netflix. We build a lot of tools internally. But obviously, as something new, we had a few requirements in mind. First, it needed to work everywhere. I don't want to neglect devices. It needs to work on all our devices, thousands of them. I need low resource utilization. Your phone, your laptop, super powerful. Doesn't matter what you say. Smart TVs, cable TV boxes, not that much. We're fighting for kilobytes of memory there. So every little bit counts. So I need something that's very, very low resource utilization, especially memory. Needs to deal with different network conditions, right? I can't just keep sending beacons, like I said. On the backend side, I need something that can handle that amount of data. Those tens of millions of devices, users, the sessions tend to be very long, normally hours and hours long. So a lot of actions, a lot going on there. So I need to be able to handle that amount of data. Ideally, something that scales horizontally to support our user growth, right? I'm planning to do a lot of analysis on top of that data. So I need some sort of fast querying because I want to query something and I get a response and I want to, hey, I want to change that and do that again. And it's a very interactive process. And I need something fast so I don't waste a lot of time. I can't just issue, hey, data warehouse thingy, generate me a report. And maybe a couple hours later I get a report back. It just doesn't work for us. I need something quick. And obviously, last but not least, something that is flexible. Our requirements change all the time, so I want to make something that is as flexible as possible and can evolve with time. Cool. I talk about real user monitoring. So by what exactly are we monitoring in this case? We decided to start simple as everything with just wall time. So time for a user to do certain action. And these are real user actions, like opening the Netflix app on that specific device, or clicking on the play button and waiting for the title to start playing, or maybe seeing the details page. So you click and then you see the description of the movie. So real user actions. Cool. Looking to monitor that, start simple, wall time. But how are we measuring that? Where does the timer actually stop and start and end? There's no standards there, right? At least not for our app. That's something that really tracks what the user is doing. End of the day, it really depends on what the user is trying to do, what he's trying to accomplish. So we started thinking from a user perspective and try to capture a few of the feelings he gets during that action. When does he get a feedback from his action? Whether something happened, right? Like it might be a spinning thing, but he at least got some sort of feedback. When can he continue doing whatever he was doing? Right? He might not be fully loaded, but he can continue doing. Like, For example, you open the list of movies, you might see the title of the movie, you might see some description, but you don't see the box art. But you can already start reading, so you're doing something, right? You can continue doing what you're doing. And when it's actually done, so you have your full page rendered. So we couldn't find a single number that would actually track all of that on all actions. So we basically created different timers that are very specific to each user action. So we ended up with a lot of timers. The ones we have probably don't make sense to you, but just to give an example, most of the navigations inside the app from one page, one view to another will have at least what we call TTI and TTR, so time to interactive and time to render, which should track the time from the user initiating the action, being clicking a button or something, up until he can start doing something again. Not exactly the same definition as the browser, TTI, but similar to that. So he can start reading the titles, and then we end the timer there. Time to render, when everything is rendered above the fold, so you can view it without scrolling. So different timers to capture different user feelings. Important for us. Play delay, though, time when you click play, those numbers, they don't really make sense anymore, right? So we created a different timer from clicking play until the first frame of the video is visible to the user, and he can actually start watching the title. So we spent a lot of time discussing what we should track or not. Cool. With that theoretical part done, we know what we want to implement, how we actually start doing that, getting like our hands dirty and getting that out in the field. So again, we started simple. Let's just start with a few very simple libraries that we can use on all our devices. We needed one for at least one for each kind of device there. So we ended up creating a few. And they do really simple things. They do some sort of session tracking. They would implement the logic around the timer, start and end, creating those events. They will implement some sort of ring buffer so I can keep buffering all those messages. Some sort of logic to decide when should I flush those events to our backend. Hey, is the network busy right now? Should I wait a little bit? Or this sort of logic. So we created a bunch of those libraries. That was pretty straightforward, nothing too complicated there. The hard part was actually implementing the timers on the devices. Not just because there's a lot of actions and a lot of devices, but also because a lot of those devices, they have nuances to them. So some TVs, for example, they support suspend. So I just put them, I basically suspend in memory. And when I bring those back, is that an actual app startup or not? We need to kind of decide that. And we need to find the right hooks in the code to define the start and end points. So that took quite a while. It took quite a bit of time to actually get that right. But we spent time, and it was definitely worth it, because by the end of it, we knew that we were capturing something that was meaningful, like meaningful to our users, and we could actually rely on those numbers. So definitely worth it, but it took a bit of effort. Cool. Those devices generating a lot of events, and how do we actually receive them on our backend so we can analyze them? Whenever possible, I want to avoid reinventing the wheel. So I decided to piggyback on something you already have. We have our data pipeline internally that we use for a lot of other things. It was trial and proven, and it works really well, it scales really well. I don't want to get into details of the data pipeline, but if you're interested in that bit, there's a link here that goes to the blog post that goes into really detail bits of the data pipeline. But we kind of piggybacked on that. So we send all the devices, send the events there. But in a nutshell, those events get to a front-end Kafka, Apache Kafka, that then gets routed depending on a few rules that we set. Some of them end up going for real-time analysis, alerts and this sort of thing, Apache Stream. Some of the data gets indexed in the Elasticsearch, but the bulk of it ends up in S3, so Amazon Simple Storage Service. So we dump everything there so we can analyze it later. That's the bulk and everything, and that's where I'm going from on the next few slides. Cool. Receiving, dumping everything into S3. And as soon as we started analyzing all that data we were getting back from the clients, we started noticing things like this. You guys probably familiar with that kind of distribution, right? Like multimodal, nicely distribution. This was good in one point because we noticed that we were kind of capturing different moods on what the user was perceiving. But on the bad side, this is a bit trickier to analyze, especially to automated systems. It's not super hard, but it just complicates things a bit more. So the next step, what we tried to do was to add more dimensions. This basically happens because we had a lot more dimensions than we initially thought. Way more modes than we initially thought. So we started splitting things until we got a bunch of those nicely looking guys here. Bit nicer normal distributions. And as you can imagine, we end up with very high dimensional data. We have a very complex device categorization system. Like which hardware the thing is running on, which platform the thing is running on, which UI is it running on that thing, which version of the UI, which version of all those libraries there. So very, very complex device categorization system. We split things by geo too, like your regions, sub-regions, countries, and areas, and cities, and so on and so forth. We have a very granular network classification dimension with ISP and which Amazon region you're talking to, which CDN box you're talking to, so we need to classify by those too. As you can imagine, we have a lot of A/B tests too, and those can affect the user experience. So we need to split by A/B test and A/B test cell too. So more and more dimensions, just keep adding things. And on top of that, even a few user actions have more specific classifiers. Like I mentioned, the warm versus cold startup. They're completely different code paths, so I need to be able to split those. Even like web pages, they don't have the notion of a warm and cold startup, but they have a notion of first and subsequent visits, and those kind of behave differently. We need to download different things, so I need to split those too. So keep adding things. Very high dimensional data. This kind of accounts to hundreds of billions of events every single day. So petabytes of data coming from just performance data coming from these devices every single day. And that's just talking wall time. When over time, we kept increasing, adding more things. So a lot of data to analyze. It's already a challenge capturing that. Analyzing that, it becomes even trickier. As I mentioned, we don't want to try reinvent the wheel. So hey, first thing I'll try is just use one of those third-party data analysis tools that we use on a bunch of projects internally and we kind of know well, and you get your nice dashboards and your graphs and your queries. You don't have to put a lot of effort into it. Cool, so just load all the data in there. Didn't work. It's just a bit too much data, as you can imagine. We even decided to pre-aggregate all of that into all possible combinations of dimensions, and still was just too many rows for that to handle. It was just very sluggish. So okay, back to the drawing board, and we need to use something we really know and understand well, duct tape and Apache Spark, to get some stuff together. We were not aware of anything that could analyze that amount of raw data live, with live queries without costing us a fortune. So okay, let's just stick to the pre-aggregation bit, and let's just pre-aggregate data in all possible combinations of dimensions. That reduces things quite a bit. With Apache Spark, so there's this pass that does that, and stores all this pre-aggregated data back into a Hive table, so S3-backed Hive table. And when I say aggregate, we started simple with just quantiles, your 5th, your 25th, your 50th, and so on and so forth. So we store that back, and then I can use Presto query engine to query that data. And that kind of worked. I was getting the numbers back, but it was still a bit sluggish. It would take a few tens of seconds to get my data back, even using Presto, which is quite fast. Okay, so but what can I do to actually make that even better? Hence comes Druid. I don't know how many of you actually heard of Druid before. Another open source project. We tend to use a lot of open source projects here. Druid is a distributed data store. You can imagine it as kind of a cache in front of a Hive table that can also do aggregations. So it can do a lot of interesting things for us. So we loaded all that data from the Hive tables, all those pre-aggregated quantiles into Druid, and we can execute the same queries really fast, generally in tens of milliseconds, and get the same data back. So that really fast worked really well. We were getting the numbers we were looking for, right? That worked, kinda. Imagine a lot of the analysis we do requires rolling up, right? And I pre-aggregate a bunch of stuff. I want the medium app startup time for all Samsung TVs, and we have a lot of Samsung TVs, so I need to go and roll those up. I have pre-aggregated data, and I go and aggregate that again. In Druid, there's generally like weighted average or averages, and you know that's not ideal, right? You can get some really, really bad numbers there. But we were not sure, so okay, let's just like really do a comparison and see how it looks. And in most cases, it looked okay. Like when we were aggregating a lot of rows and we were looking mostly at the middle of the bands, like your mediums and your like maybe 25th, 75th there, it worked quite well. But once I go to the ends, to the tail and the head of the distribution, or when I'm not aggregating a lot of rows, things can get really ugly. The numbers were way off sometimes, and that can lead us to some really bad decisions. So I couldn't live with that. I just don't want to the burden of people making bad decisions on me. So how can I actually solve that? I get a bit more precision without having to go through the whole like raw events. Hence comes like data sketches, and that's the slide I like the most there because I managed to get a pug there. So if you like, not many people probably here know about data sketches or ever heard of data sketches. More of a data analyst guy thing. But in a nutshell, a data sketch is a data structure that kind of vaguely resembles a much larger data set, like a sketch, right? But it still preserves like the basic characteristics of that larger data set. Right? But is a lot smaller and a lot faster to operate on top of. Yeah? And it's okay, it works really well if approximate results are okay, if you don't need like exact numbers. And for us, that's fine. As long as I can get a number that's precise enough, I don't need the correct number, as long as it's precise enough, right? There's a lot of data sketches around. Yahoo has a few. We opted going with T-Digest, another open source project there, which is really good for rank-based statistics, like quantiles and histograms and all of those. So it works really well on those cases. It's really good, too, because it can be easily parallelized. All of those individual sketches, which end up being just blobs, I can merge them. So I can distribute that merge until I actually get to the final data sketch, and I can extract all the statistics from them. So really, really fast and really precise approximation. And the other cool thing about T-Digest is that I can fine-tune it. I can make the sketch bigger and get better precision, or I can make it smaller, get less precision, so I can kind of fine-tune it. It works really, really well in cases like that. So we kind of paired T-Digest sketches with our previous solution. So Spark would not aggregate the quantiles anymore. It would aggregate the T-Digest sketches, the blobs, and send that to Druid. Druid obviously doesn't support T-Digest sketches by default, so we had to create our own module to do the aggregation in Druid, which basically is merging the sketches and then extracting the data and getting that back to us. That worked amazingly well. A lot more precise, a lot more precise. Worked really fast, still tens of milliseconds to get most of our queries back. And this is basically the solution we ended up sticking to. But Druid has its own DSL for querying. It still has an HTTP interface, but I don't want to go and teach. Like, we're not the only consumers of that data. I have UI engineers working on that. I have guys working with ISPs consuming that data. I have a lot of people consuming that are interested in that data. So I don't want to go and teach them how to use the Druid query language to get the data they want out of that. So we ended up creating a nice looking UI to spread the word. For all those teams and make it a bit easier for them. Nothing fancy, but super powerful. You can slice and dice by basically any dimension I mentioned before. You can group by anything. You can filter a bunch of stuff out. There's a lot of different visualizations to it. You can build your own dashboards. So pretty flexible. And don't want to get into details of the app itself, but I'll just go through a few very common use cases that our users have. Being the first one, comparisons, right? You want to compare something. Is that something faster than the other one? This is a simple line chart. You have passage of time over latency here, duration, so the highest, the slowest, not good. This, in this case, I think is app startup. I'm only comparing mediums, all iOS devices, and I'm breaking by country, and I only filtered 4 countries. I don't know if you guys can read that there, but I have Brazil on top, I have India, Mexico, and then United States there. You looked at this, like giving our architecture, something smelled funny here to us when I was looking at this. This doesn't make a lot of sense. I know exactly where my caches are, and I know where my AWS regions are. It doesn't make sense that India is actually faster than Brazil. That's kind of interesting. And I want to bring that up because if I just add another filter to it, I filter by only a single device, iPhone 6X Plus. Things kind of change. Like India goes all the way up, and then you have Brazil here. So you guys have any guess why that happens? Why we see that thing? The device bias, right? It's device bias in our case. It's just that the UI is super powerful, but you need to know what you're doing there. Because you can get to really wrong decisions if you're not really careful on what you're doing. So if you decide to go that route, pay attention to like how much power you give the users and how much they know about what they are doing. You can get to really wrong decisions. Different visualizations, like we have heat maps and histograms, and I really like this inverted CDF graph. It's really cool I like it to compare things that are kind of spotty all the way around. Basically in this case, you have the durations here and the percentage of transactions that finish under that amount of time here. So different visualizations, super flexible. In some cases, makes it a lot easier to visualize and find issues. We do the same thing with A/B tests. I mentioned before, we like to compare A/B test cells. If I'm doing some sort of performance optimization in a device, we don't really release anything that to users that was an A/B test first. So I launched this A/B test with different cells, with different levels of optimization, and I want to compare the cells, and I want to see which one actually gives the user a better performance for that action. Then I can do that pretty easily using Icarus. Few very specific views. I mentioned the warm versus cold. Sometimes I can just optimize the times. I can make cold startups faster, but I can also improve the rate of warm startups, which are a lot faster, right? So I want to keep track of those. So I have a few unique things for our use cases that I added to the UI too. Anomaly detection, very important. We found a lot of really cool things just browsing to that and issuing queries. A lot of issues we fixed, but at the same time, we missed a lot of things too. We just have too many combination of dimensions to analyze manually all the time. It's just impossible. So we invested a bit of time to get anomaly detection running on those time series. So time series of all possible combinations of dimensions. You don't have to go super fancy. We started with just simple standard deviation analysis. That was it's the simplest thing you can do. And it already yielded some really cool results. We found some interesting things. And then afterward, we started getting fancier and fancier. But if you have too many dimensions, you have to check that all the time. Invest time in anomaly detection just helps a lot. We get alerts, say this looks funky, so we go and analyze a bit further, and then we find a lot of things we would never have found just by browsing in the app. So anomaly detection. Almost there. So far, I talked about wall time, right? So just time for a user to perform some sort of action. This was the beginning. We started with that. And with time, we started adding more and more things, like method tracing, statistics around network requests, and those tend to be more high-frequency events, things that happen too frequently for me to just start creating events, putting that in a buffer. It would just fill the buffer right away, and I'll be screwed. So what do I do with those high-frequency events? I take, for example, network requests. I can capture a lot of stuff from network requests. I can get the total duration of that request, the request size, like response size, SSL handshake time, DNS resolution time. I can capture a lot of stuff just from network requests, which is really important for us, especially for our teams working with ISPs. Really, really important information. We really want to gather that. But I can't just create events for every single network request. So how do I deal with that? Obviously, you might be thinking, hey, you might just go sampling, right? We're not big fans of sampling. All that data that I mentioned before, that's not sampled at all. Like, we just get every single event. And we do that for a few specific reasons. Getting sampling right is very tricky. Doing sampling is easy. Doing sampling right is hard. Plus, we don't want to miss rare events, like things that, hey, this specific Android device on this tiny ISP on this tiny country, we don't want to miss that tiny thing. We want to actually be able to find that data. So instead of sampling, we went with a different approach, which is pre-aggregating things in the client and then sending that data back less frequently. And when I'm saying aggregating the client, I'm not talking about just calculating the average for the hour and then sending that back. As you know, I'll be re-aggregating things, and that's not good. I really want to see the whole distribution. So we went with this guy here. Frequency histograms work really great in this case. I know Chrome uses the same approach on a lot of things. And basically, you have a bunch of buckets of specific times of numbers. In request size, it might be the size of the request, but specific numbers there. And every time an event happens within that bucket range, you just increase the count and keep counting. And then every hour or so, or whenever possible, we ship that data back, and then we analyze that in the backend. So we aggregate, collect that in the client. Cool thing about that is that for our resource-constrained devices, it has flat memory use. And we can fine-tune that to the device. If I have plenty of memory, I can increase the number of buckets and get more precision. If I don't have that much, then I have less buckets, I have less precision, but it's flat. It doesn't matter how many events I get, I just keep adding to the count as long as I don't blow int. But it doesn't happen. Very fast to operate on too. I just keep increasing count. Very, very, very simple. So work really, really great for our resource-constrained devices. But there's a gotcha here. Memory depends on the amount of buckets I have, right? Not the amount of events. So you can see a lot of holes here. So that's just wasted memory. And we're maybe not getting enough precision where most of the action is happening. So how can we do it and go and improve that a bit? So we borrowed not an idea from Chrome. Jim Roskin has a great talk about it, which is using exponential bucketing. Works really well. You have really tiny buckets where most of the action happens. So you have higher precision there. And as towards the tail, the bucket size increases. You don't lose that event. You're still capturing that, but you lose precision a bit. But that worked really, really well for us too. So exponential buckets. Using basically the same approach we had before. Spark to aggregate things, Store to Hive, Load to Druid, UI to query things. And then we get some pretty graphs like that. We have some nice heat maps. This is DNS resolution time. On the x-axis there, I have a few hours of the day. And then I have the DNS time, the time to resolve DNS there on the y-axis. And the darker the color, the more samples within that bucket, right? This is US, very nice and uniform, good looking, right? And then you go to the rest of the world. Things are all around. And this is really important information for us. So we can go and slice and dice this even more, and we can start working to improve those. We can do things like that. Bubble chart, very similar to line chart, but then you have the size of the bubble, which represents the size of the population. This is, I think, is transaction duration to AWS for specific requests on 4 large US ISPs, where we can, like, on the x-axis, we have hour of day, and then the duration there. And you can clearly see that specific hours of the day, we see degradation in most ISPs, and that's generally due to congestion in that ISP. So we can go and start working with those guys. I don't have to look at times. I can look at counts too. I find some interesting things there. This is the amount of DNS resolutions per device, per like single user device, and then group by the kind of the device ID, what we call, right? You can clearly see 2 bands here, right? You have a top band, like all wide, and then on the bottom. I think the bottom is smart TVs, and the top, I think it's gaming consoles. And this is an interesting issue we worked a while ago, where few devices had issues with DNS cache, and that were resulting in a lot more DNS requests than they should. So we found that, worked on that, make things a bit better. And I think that's about it I had for today. Do I still have time?
Yeah.
2 minutes? Okay, cool. Okay, let me actually do something else. Cool, I have time, I have to. So with that information, we actually got a really nice map of the internet, at least to regards to how it actually talks, all the devices talk to our backend services, right? So how can I actually use this information directly to improve our product, right? I can just go to developers, see this the red number here, just go make it better. It just doesn't work. Engineers are really great at solving problems if they can see the problem. So just showing a number is not a problem, it's just a number. So how do I actually use that information to make it better for the user, to make our developers improve that? With that information, with that map, all that information we captured from network statistics, we created what we call the magic modem, which is exactly that. It's a physical box. Where are you? It's a physical box that can simulate any ISP that we have customers on the developers' desks. So we built a bunch of those hardwares, and we gave it to developers internally so they can reproduce every single ISP on the planet and see how that feels. And let me see if I can actually play this video guy thing. I'd say I didn't have a video, but let's see. All right. So this actual device, I'm simulating here an ISP in Kazakhstan, right? Opening the Netflix app, everything looks pretty good, right? Netflix main page works fine. ISP, Kazakhstan, this is a bookmark, second ISP, all good. Clear everything. Should speed that up. Then I go and change that to a different ISP. That's an ISP in Cameroon. Different network characteristics, as you can imagine. Kazakhstan is not great, but Cameroon, yeah, it's kind of tricky. And then we try to open the Netflix app. And then we wait. And then we wait a bit longer. And we keep waiting. And there's not much there. Eventually something will show up. Eventually. There you go, there's something. So what I want to bring with that is that this helped tremendously internally. We capture this data, and we can use it not just to monitor things, but also bring that issue to the developers. So once they see that, once they experience that, they feel it, and they can work to make it better. And at the end of the day, is not that hard in most cases. Like sometimes they just make stupid decisions because they are used with the nice 500 gigabit connection that we have in the office. So different worlds, and they need to kind of experience that. And that's the thing all I had. Let me go back to my previous slides. And there you go. So I don't think I have time for questions, but I will be here after the reception if you guys want to chat and exchange some ideas. My contact information is there. Feel free to reach out, add me on LinkedIn. I'm always happy to answer questions or or discuss anything performance related. That's about it. Thank you.